Hi everybody, today I would like to talk about an approximation. So just a simple one. We will just discuss square root of x is approximately x plus y divided by 2 square root y when x is close to y. So this is the notation I will use, close to notation. So just an example so let me call this as a fact. Why this is true I will discuss in a few minutes. So let me just, for example, let's look at this square root of 24. Let's take y to be 25 so that we can calculate the square root of square root of y in here. So then in this case we have 24 plus 25 divided by 2 times square root of 25. This will be 49 divided by 10, which is 4.9. So 4.9 is the approximate value of square root of 24. If you use your calculator, you will see that square root of 24 is 4.8989 and 79 and so on, 794. So up to 4 decimals it's like 4.9 actually. Very good approximation. Let me talk about why this is true when x is close to y. In here like 24, we can do this because 24 and 25 are close to each other. So this is your x value, this is your y value in here, 25. Alright, let us discuss the proof of this result. The simplest one you can go with is just a perfect square. We know that x is close to y. In this case, square root of x is close to square root of y then. So if we just look at their difference, square root of x minus square root of y will be close to 0. Now if I square both sides, then I know that this complete square is close to 0. If you expand this out now, then you get x minus 2 square root of x square root of y plus y is close to 0. If you solve for square root of x from here, you can just say square root of x is close to x plus y divided by 2 square root of y. Alright, so it makes sense. This is the case when x is close to y, right? Alright, so another way of seeing this result is using linearization. Let me show you that too. What if I look at y and x in here? What if I look at a function, graph of function, let's see. So let's say this is y equals f of x. And if I look at the linearization, meaning that the tangent line at y, so let's look at this point y and then f of y. So this point is y f of y. I'm going to draw a tangent line at this point, passing through this point, of course. So we know that this line is y equals L of x, which is a tangent line. If you write it down, then because we are writing this at y, so it's going to be f of y plus f prime at y times x minus y. So this is your L of x. We know that when at point x, let's take a generic point x in here. Capital X. Then if you look at the value at L of x and the value at f of x, they are close to each other as you see. When y is close to x, so this value is f of x in here, the other one is L of x. You can see that f of x is close to L of x when x is close to y. otherwise not correct. So y is just a point like we fixed first, close to x. Okay, let's use this now as an application. I'm going to take f of x to be square root of x. Let's take f of x square root of x, then its derivative, we need its derivative at y, f prime at y. So f prime of x is equal to 1 over 2 square root of x. Okay, now let's rewrite this expression. So we know that f of x is close to L of x. Let's write L of x, which is f of y square root of y plus f prime at y 1 over 2 square root y times x minus y, x minus y. Okay, now let's simplify this. What is f of x? F of x is square root of x. Now what we observed is that, so when x is close to y, we have this approximation. So let's rewrite this. Square root of x is approximately, so this approximation sign in here, approximately square root of y, which is like if I multiply and divide both sides by 2 square root y, then I will get y over 2 square root y. Okay, 2y, right? And then plus, this one is x minus y divided by 2 square root y. If you simplify the numerators, then you will get square root of x is approximately x plus y divided by 2 square root y when x is close to y. So this result is also, like, as you see, it comes from the linearization. Very nice result. It comes from, like, heuristically, it comes from this perfect square too, and that's it.